So hi, I'm Jackie. As Kyle mentioned, I'm with Lamont right now. I'm with their kind of tropical cyclone modeling group. So yeah. Um, all right. So to start out, the region that I've been studying, we're doing a project where we're basically looking at petrochemical spill risk in the Houston Ship Channel. So this is the topography of the area. Houston is out to like the west of this, but like basically you can see that there's a channel that comes in through this is like kind of Galveston Bay area and it goes um basically up through Trinity Bay or Galveston Bay, and it comes straight into Houston, basically. So there's a lot of storage tanks here. Um, there's a lot of like petrochemical tanks. It's one of the biggest in the U.S. And if you zoom in like over here, just on Google Maps, and I like to do this for fun sometimes, just like you can actually literally see all of the tanks, right? All of these circles that you see, like these little guys, like all of those are tanks and facilities along this kind of area. Um, so there's definitely a lot of asset exposure here. And at the same time, obviously Texas has had some very intense hurricanes. There's been like Hurricane Ike and Hurricane Harvey and stuff like that. Um, and the other interesting thing about this project is we don't really know what's in the tanks. We have some estimates, but like they're very kind of like wishy-washy because of other kinds of restrictions from like where we're getting our data. But you can see a couple of them, like you have like acute toxicity and combustible and all this kind of stuff, like flammable. So these are some of the hazards of the things in the tanks. So yeah, this is going to be the kind of workflow. So first, we're going to simulate surge and wind for 2100 synthetic storms. Basically, the storms are the tracks are originally generated using CHAS, which is Columbia's hazard model for generating like statistically dynamically downscaled kind of storms. And we use a Holland 80 wind model to, get the wind field. Um, the the thing to note here is that it's kind of a really big sample. I think a lot of I haven't been in this field for too long, but a lot of the work that I see looks at like a handful of storms or even up to like 100 or 200. This is like 2100 storms. So it's going to be, you know, a lot of things and we could do statistical analysis and stuff. Um for spill specifically, what I'm going to do is basically find 15 storms that are closest to what we find to be the 100-year surge. And later I'll repeat it for 25 and 50-year. For all of those, we're going to identify like the profile of the surge using like gauges, and then we will basically resimulate the storm again. This time using fixed grid outputs to record like the flow fields. Then we use those flow fields to do Lagrangian particle tracking of the kind of spill trajectory. And finally, we haven't done this part yet, but we have another person on our team with a fragility model that basically kind of calculates the probability of each tank failing and factors in like actual volumes to what each marker represents. And then at some point, we'd like to figure out what's actually in the tanks to determine like public health hazard. So the setup is this. This is the region. All of the red dots are tanks. You'll note that the tanks are actually really closely spaced together. And just to make sure we can resolve as best as possible, like the effects of topography and height, we want to use high res output. So we also are going to place 8,000 gauges, one in each tank. The IO of this has made my cluster manager very mad. It actually takes a lot, and it is a consideration for when we run things. After that, we're going to use, or on top of that, we're going to use fixed grid monitoring to get like uh, surge planes and flood planes and stuff. And then obviously we're running a lot of storms. So how this kind of worked in practice is I ran them in batches of 100 on our computing cluster. The average runtime is about 2 to 3 days a storm, and the post processing scripts were very important for this because you can basically reduce a lot of the output by at least a factor of 100. Because for the gauges, what you want to do is basically as soon as you finish the simulation, you can delete all of the gauges that didn't get new surge because the vast majority of them won't be flooded in most simulations. And for the fixed grid, you can just download the ADA field from the generic kind of fixed grid monitoring output, and you can kind of compress that, and that'll substantially reduce kind of costs. So after doing all of that, this is the return floodplains that I found. So this is 25-year and 50-year and 100-year. In each kind of figure, you can see the red dots show the tanks that lie within the floodplains. And in the insets, I show the kind of distributions of floods that are at these tanks. So there's like 150 in the 25-year, and that goes up to like about 700 tanks flood in the 100-year scenario. And the floods vary between like 0 and 3 meters, depending on like where the tanks are located, basically, and their elevation. So we have that. We can also calculate the return surge by calculating like basically the surge height from every storm and doing a return period. So doing that, we get like where the 100-year kind of storm is, and we can look at the 15 storms that basically have surge closest to that. So, and to set up the simulations, basically I'm gonna record the flow field once every 4 hours. So you can see here, these are the surge profiles for each of these storms, and the dots indicate like when I'm recording the flood. Yeah, that's basically the setup. And now we can look at a spill simulation. So how it works is I get the flow fields, and you can see the resolution of like how fast I'm recording the flow fields by like the flood is changing once every 4 hours. But you can see that the markers are changing at a time scale much smaller than that, and also a spatial length scale that's much smaller. Basically, there's built-in functions in fixed grid monitoring that allows you to interpolate your flow field in both time and space. So we can interpolate to 20-second intervals to get the flow, like for the flow field between our like 4-hour recordings. And also you can interpolate to the exact location of each marker. So what I've done here is basically I've placed 25 tracer markers at each tank that floods in the simulation. And then I let the flow go, and the marker is basically advected by whatever velocity we find from the fixed grid outputs, which is like the surge velocity. And then also there's a random walk component to add in diffusion. I think it might be a little too high because there's a little too much wiggling here. But yeah. So that's one spill simulation. You can turn that into a kind of spill density plot. By basically you can divide the image up into little cells, and then at each time step you can count the number of markers that are in the cell. So in this case, I have 0.002 square degree cells. One thing to note is that we haven't accounted yet for like what's actually in the tanks or expected spill volume. So for the rest of this kind of talk, we're going to be basically working in terms of like marker density and not actual like volume. If you look at all 100-year storms, they're not all starting at the same time, but you can actually see that they all kind of have a similar pattern. And that kind of makes sense because they all are going to have similar surge, like heights. So the only thing that really changes between these storms is like the shape of the profile. So you can see that some, like the storm comes and immediately everything floods, and there are some where gradually the water rises and falls. But yeah, you can kind of see patterns. So if we look at this and take the average of the final marker density, or wait, the marker densities also look similar, which makes sense. It means that if you look at the marker density at the end of each simulation, it kind of tells you where all of the oil particles have like ended up, or oil chemical particles. And if we take the average, we get an idea of at this kind of level of storm, like where does the oil end up? So you can see that it kind of matches a little bit like what we saw in the simulation. So if you look here, you can kind of see that surge comes in, this cluster kind of goes around the coast. The oil over here gets pushed out over there and that kind of stuff. And then if we look at the mean density, we can see similar patterns. So this is kind of the distribution of an average oil spill at this level of hazard. Oh yeah, for comparison, here's one of the individual storms. So you can see that each of the storms kind of looks like the average, I guess. The other thing that I did, which is interesting, is marker density is really useful, but we can run into issues where, well, basically, we also should be interested in areas that the spill is just passing over, right? Because another thing is we're not factoring in a lot of things, and one of the things we're not factoring in is sedimentation. So it's not really clear, like, while we can look at where the markers end up, it's not clear where a lot of them would land if you account for the fact that, the chemical is sinking. So as it passes over, it's likely that you're going to have some chemical or oil or markers, would land kind of on the area that you're passing over. So what I kind of did is I tried to measure duration. For each kind of cell, I counted the number of frames where the cell had at least one marker inside of it. So at the end, what we get is we see kind of these really dark areas, like this is in hours. We see these really dark areas kind of like where we saw that the spill density was really high at the end, because after the simulation, all the markers are just kind of sitting there. So they're there for a long time, obviously. But what we also see is these kind of transient areas where the spill kind of passes over. Um, I don't see it in this particular kind of simulation, but when I was looking at really, really strong storms, like thousands of year kind of return period, what I would kind of see also is there were some storms where a lot of the markers literally just got pushed north, like over here, they just got pushed north over land. So you also had little traces where basically the markers weren't ending up, but they were passing over large areas of this kind of land. Um, I think it might have gone a little too fast, but yeah, these are the durations for the individual storms. Basically, um, they all look kind of similar, but in this sense, you can see more variation because the shapes of the profiles changed a little bit. So in this kind of transient area, you can see different patterns for like where are the markers kind of hanging out during the actual like impact. So for next steps, basically I have we're working with a couple of different universities for this project. One of the teams is at Rice University, and they're working on a fragility model. So I actually got some preliminary data for that like a little bit ago. And basically what that will do is in addition to looking at which kind of tanks are flooded, we can look at like the actual expected spill volume so that we have a better estimate of like what's actually coming out of the tanks and what the material is that's moving around. The other thing that we need to do is figure out what's in the tanks. Basically, our situation is that our contact has gotten like a log file that I guess first responders use, but like it's very incomplete. It only lists hazards by like zip code. It's like very kind of you don't know like which tank is which and like how many entries there are. So we're working on trying to make an estimated guess about that. And then the third thing, which I'm quite interested in, like we were talking about just earlier, like kind of debris fields and kind of landslides, looking at kind of more advanced particle tracking models because there's a lot of stuff that we're missing here. Like we don't even have like concentration dynamics. Like it's purely vective. Like if there's a large concentration of markers in one area, normally you'd expect like that spill to like spread out, which it kind of does by diffusion, but it's not really related to the actual concentration. So yeah, there's a lot of